Hello everybody! I hope everyone's having a wonderful day. So today I'm going to be talking about a new topic. So it's still a part of the same general broad look of where we are, but we're going to be focusing on a different kind of structure called a graph. So this next major part of this is involving so-called graph algorithms. But before I can do that, I have to talk about what a graph is. So graphs are fundamental combinatorial or mathematical objects of much study in the mathematical sciences. So these are not just used in the context of computer science, they're very heavily studied mathematical objects among all the mathematical sciences. So this is a mathematical object that's been studied many different areas, different aspects of them have been studied. We're going to be interested in their combinatorial aspects in relation to, for example, algorithms. So we'll specifically talk about algorithms that we can use on so-called graphs. Now you might ask, why would we want to consider graphs? Surely we have lots of tools at our hands that talk about different problems and how we can solve them. But I must stress that many problems of interest for computer scientists, mathematicians, statisticians, and so on, many of their problems, many problems can be modeled using graphs. So the concept of a graph itself isn't just functional, as in we're going to talk about algorithms for solving problems on graphs. We often will use graphs to describe problems. So by understanding what a graph is, it opens up a whole new cascade of problems they may or may not have thought about before in the same context we've talked about other topics in this course up to this point. So just to give you a couple of examples of, say, things that you may be familiar with that you can model with graphs. For example, here I have a computer network. So I have some servers here and I have some clients. But notice here that I have some connections between servers and clients. Some of the servers are connected to each other. In fact, all of them are. But the point here is that I don't really care about the positioning of where the computers are in my picture. It may be a practical consideration, but for us, the connectivity between, say, a server and a client would make a big difference. So if there's a link that connects a server to a client, for example, maybe the assurance that they're going to be provided a service. In contrast, another example, and I must stress this computer network example, something you're going to see a lot in other parts of your studies potentially if you're interested in networking. Learning about graphs is it's a valuable tool. It's not just the mayonnaise. It's a very good mayonnaise for understanding how networks operate and what you can do with a network. So another example here is a so-called flight routes map. So here's just a graph that represents the connections between different airports. And it has numbers on these to represent distances between those said airports. So naturally, I can ask questions about the structure of this. So for example, I can ask, if I'm at this airport, how many kilometers does it take me to get from here to over there using the least amount of distance, or equivalently, or possibly, least amount of fuel, reducing the cost of, say, flights from, say, hopping from one airport to another airport. Another more simpler way of thinking about this is perhaps you're thinking about going from point A to point B in a town. You can imagine these yellow dots I have here as different, these make up the road segments. So suppose I start right here and I want to know the shortest way I can get over to that bottom right corner. What I could do is I can model my streets using a graph that's comprised of these yellow dots that represent, just like my servers and clients or my airports over here, I can use these to represent kind of essentially intersections or so-called dead ends if there isn't an intersection there. And I can use the roads to tell me where they connect to each other, just like in my network, where I have connections between the servers and the clients. And in my airport example, where I have airports connected to each other based on having a flight there or not. So graphs are, I would argue, quite natural for talking about many different kinds of problems. There was a graph theorist I knew back in my undergraduate years. The motto that he essentially had in his research was that if there's a problem, there's very likely and high chance that you can model it using a graph. So what is a graph? So before I get into the formal definition, the big thing I really want you to notice is that, for example, in my picture here, of all these flights that could go between them with my numbers here that represent the distances, these distances, they don't really have to really be true distances. And notice that they don't necessarily reflect how far away they are. So for example, notice this 535 is to here, but notice it's 4,184 there. There's no geometric meaning imposed on my graphs. I can impose such meaning if I would like, but keep in mind that at fundamentals, we care about the airports, their connectivity between them, and we may impose or add additional information so that we can learn more about either the structure of it, which we use to formulate a problem, or we might be using it to, say, model something of interest for us. So let's talk about, so just as an example, I could have easily just taken, so notice I have all these clients and I have the servers here. I could have easily just replaced these with circles, gave them names, and it wouldn't have made any difference from a graph theoretic standpoint. So just remember that graphs, it's more about the connections between sites or roads or airports and the meanings that we impose on the structure of the graph. It's connectivity, what we're going to refer to as vertices and edges might mean in the graph. So there's many, many things we can do with graph theoretic ideas like these. And I always get very excited because this is a topic, especially as site speed. So I'm hoping that a little bit of that will shed onto you if you find this topic interesting, whether it be for functional reasons or just that you find this topic interesting in its own right. So let me just put this down here. So anyways, I'm going to give you the definition of a graph for our purposes. So a graph is a pair, capital V, capital E, or VE, where capital V is the set of vertices. Now I must stress that I call them vertices or we call them nodes. Sometimes it's convenient to call it one or the other. I'll usually refer to them as vertices in this context, but if I use the word node, that means the same thing in the context of a graph. At least, unless there's a specific meaning imposed on those words. I must stress that the singular term for a vertex, so this is a plural term, a pluralistic term. This means many vertices. There's more than one. If I have a single one, it's called a vertex. I must stress that it's called vertices as a plural. Singular is vertex. It is not vertexes. Don't say that. That's not quite right. It's not called vertexes, it's called vertices, or nodes. And we have this E here. Capital E is the collection of pairs of vertices. So these are going to be what those, so for example, when I had the connections between my two airports, that's an edge. If I had a connection between a server and a client, that's an edge. If I had a link that gets me between those two yellow dots on my roadmap, that's an edge. So I'm going to have a collection of these. These are comprised of pairs of vertices. So I have U and V, for example. Those are two vertices in my graph. I call that an edge. Now, I'll usually write it more broadly using U and V with ordered pairs like that, written such as this. So for example, if I had edges U, V, if I wanted to talk about the definition itself, I would usually use this notation. But if I have some specialized imposed meaning on the graph, which will typically happen, I often will write the edges a little bit differently, as I'm going to mention in a moment. But as a sake of convention, when I have one of these graphs, the convention is going to be, if I use lowercase n, that refers to the number of vertices, and the number of edges is m. So note that these bars just represent the cardinality, or the number of elements in that set. Just like this one here. So, just as an example, here is an example of a so-called undirected graph, where it has vertices. There's A, B, C, D, E, and F. Note that the order I described them over there in that set doesn't matter because it's a set. The order of the elements are given doesn't matter. But the other thing I want to point out is, sorry, don't mind me. I'm putting this back up here. So those are the vertices, the edges, notice the connections between, for example, A and E. This is an edge. A and B, this is an edge. Notice that I have a line that connects them. That's an edge. So that's telling me that A and C have a link that connects them. So I refer to this as an edge. Now in an undirected graph, as I'm going to mention in a moment, I normally write these using curly braces to indicate that they're undirected. We're going to have various different kinds of edge types. So we're going to have so-called undirected edges, and we're going to have directed edges. So I just want to point out that sometimes people can write the edges a little bit differently. So if I don't want to impose a direction on the edges, as we're going to see in a moment, I sometimes would write these with curly braces to indicate that they're unordered, meaning that it doesn't matter if I read it from A to B or B to A. It doesn't matter. So the natural thing is, let's talk about these edge types. So this is just an example of one of these graphs. Believe it or not, if you've got the intuition, you can see how I can make graphs for these two over here. So let's head over here. Just gonna move that over here. So one thing I really want you to notice is that what I've wrote over here, like with these are all vertices in the graph. And the edges that tell me to go from one airport to another, this is an edge. And I've included in this graph, this is an example of what we're going to talk about later as a weighted graph. I could impose weights or costs on the edges that may represent something special for my problem. So in this case, the distances between the airports. Likewise, if I have this graph over here, so keep in mind, this is really just a graph that I have sitting in front of me. Each one of those is just a vertex. The computers and the servers are they're just vertices in my graph, and the edges are the links that connect the network. So let's talk about edge types. So given an edge, E is equal to UV. So I'm going to be laying out a bunch of terminology. So this will be the way that we're going to talk about the concepts of graphs. So this terminology, as grueling as it might be if you've seen this before, I have to go through it so that everybody knows how we're going to talk about these graphs. Because there's a very specific way we talk about the graphs sometimes. And everybody sort of has their somewhat different deviating conventions for what they use. So I'm just laying out some terminology for us. So given an edge, E is equal to UV, where U and V are the end points. So if I give you an edge, I'll refer to the two vertices that connect together to make that edge as the endpoints, are the endpoints or end vertices of E. So if ever I'm talking about an edge and I want to tell you what those two vertices are, I'll refer to them as their endpoints, or if I want to refer to one of them, I'll call it its endpoint. So, there are different kinds of edges. So there are different kinds of edges. And these different kind of edges tell us what kind of graph we're looking at. So notice how I talked about an undirected graph over there? This is because of the edge types. So I'm going to talk about that. So the first kind, and this is going to be the kind we'll mostly focus on, are so-called when we have graphs that have undirected edges. So undirected edges. So this is an unordered pair. An unordered pair of vertices. Unordered pair of vertices. U and V. Denoted as UV like this, or UV. I must stress when you use the rounded parentheses, I recommend that you make it clear that the graph you're talking about is undirected. This is because there's another type of edge that imposes an ordering on the endpoints, which is called a directed graph, which I'll talk about a little bit in actually just a short moment. So it usually makes it a little easier to tell that you're talking about an undirected graph if you write it like this. As long as you just make it clear you're talking about undirected edges, at some point it should be clear regardless if you use this or this. That's my point of being clear with you. So the big thing here is that the order of the vertices does not matter. So if I give you UV with the curly braces, like this, UV, so this is the same as VU. So these are the same exact thing. That's why I usually use the curly braces, because if you know a little bit about set theory, you know that when I write out a set, like if I write out a set, the ordering of them doesn't matter. So this is pretty helpful to remind yourself of this. Okay, naturally there's the so-called directed edge. If there's an undirected graph, undirected edge, there has to be a directed edge. So this is an ordered pair. An ordered pair of vertices. An ordered pair of vertices, UV, where U is the first vertex so this is sometimes called the origin or tail sometimes. So if you need to talk about which vertex, because it'll be pointing in a direction as we're going to see in a moment. And the second vertex is V, which is sometimes called the destination or head. And is sometimes called an arc. So if you ever talk about directed edges, very commonly they will refer to them as arcs. Because it's short, sweet, just like edges is very simple, like undirected edge is a little bit longer. Some people refer to edges, usually meaning the undirected edges. If they want to talk about a directed edge, they'll usually say that. Or they'll call them arcs, for example. Just be careful when somebody's describing this to you. And sometimes called an arc. So if E is equal to the directed edge UV, now this is an important piece of terminology here, then edge E is directed from U to V. This is abbreviated, so I'm going to abbreviate this as U with an arrow V like this. So just to give you a clear picture of what these edge types look like, here's the picture. So if I'm talking about an undirected edge, so here's an undirected edge. So here's what an undirected edge looks like. So if I give you UV like this, it just looks like that. That's an undirected edge. Now, a directed edge, so if I give you a directed edge, so remember, if I put VU, it doesn't matter. This is the same edge. However, the ordering does matter when we talk about a directed edge or arc. So if I talk about a directed edge or arc, so if I give you UV like this, What this is saying is that it's directed from U to V. However, if I give you VU, so if I have UV like this means it's directed from V to U. So those are the two main edge types that we're going to talk about in this class. So those are the two edge types. Now, one thing I do want to make a remark about is that it's a very common thing to do is if you ever want to take directed edges and write, so if I give you, say, an undirected edge, and say you want to describe it as a directed graph, like more broadly, because remember, it doesn't matter, if I'm at an undirected edge, I could go here to here and back, right? Like this. I could go back and forth. The direction doesn't matter at all. However, notice that in a directed edge, I go from U to V, I don't go from V to U. I'm gated off from it because the direction of the edge. So if ever I wanted to make something that looks like an undirected edge using directed edges, notice that I could just do this. So I can make two directed edges pointing at each one of them. So I can make an undirected edge from two directed edges. So notice now I could go from U to V and V to U, just like I have for the undirected edge. So this is just a little technique I just want to point out. It's very standard. So if you ever have yourself a directed graph, so what we're going to talk about is a graph with directed edges, and you want to make it operate just like an undirected graph, which has undirected edges, you could just simply mimic this by using two directed edges like this. So many times I'll just talk about undirected graphs, and oftentimes if you want to talk about it as a directed graph, then you just simply would use this kind of construction. So you would just double the number of edges just by doing this. But I must stress that it doesn't change anything. However, here's my big point of warning. This is a very big warning. If you have a representation of your graph, remember I talked about problems being formulated as graphs. So these edges and how they're formulated makes a very big difference of what we're representing as the graph. For example, if we had our flight map, right? Now in our example there, if I were to represent, say going from, say, Winnipeg to Vancouver or Toronto, if I were to use that representation, it wouldn't matter here because it would be no different if I went from Winnipeg to Toronto or Toronto to Winnipeg. I would just use the same distances on both of these. However, in some problems, being an undirected edge actually might mean something very significant. Meaning that by imposing two edges like this, you may actually completely destroy the representation of the actual problem itself. It may mean something completely different. So just be very wary and remember what the problem that you're considering is formulated as in terms of the graph. So sometimes these ideas of translating from one graph to another they may lose their meaning, just to be very clear. So let me just lay out some definitions of graph types, as I've sort of alluded to here. So there's three main types I really want to touch upon. So just keep in mind the intended representation of the graph. Sometimes you can expose some special structure of a problem based on using a graph, but that doesn't necessarily mean that by imposing an additional structure to the graph from your representation, you're going to still maintain what you wanted to represent with the graph anyways. Because sometimes these edge types really do matter. Sometimes the way you connect the edges between other vertices might matter in your problem. So there are several kinds of graphs. So these aren't even all of them. These are just the most common ones you're going to probably run into. So there's undirected graphs. So this one's going to be the one that we're going to primarily focus on. But I just want to make sure I touch all bases, okay? So an undirected graph, very simply, is a graph where all edges are undirected. Seems very natural, right? you'll find that most of the terminology in graph theory is very intuitive like this. A directed graph. Now, some people like to call directed graphs digraph. So if I have a digraph, that means directed graph. So this is just simply a graph where all edges are directed. And then we have mixed graph. So sometimes you run into these. It's called a mixed graph, naturally based on the edge types I've talked about. So it's a graph where edges are directed and undirected. So that means that there might be some edges in the graph that are undirected and there's other ones that are directed. Sometimes these may actually have a special meaning, like akin to my warning that I mentioned earlier. Sometimes an undirected edge might mean something special in your problem that you're formulating using a graph versus the directed edges. Or a graph where edges are directed and undirected. Hence its name. It's mixed. Okay. Now, another notion I need to talk about is so-called adjacency versus incidence. This is another core relationship that graphs have with respect to parts of them, namely the vertices and the edges. So we got to talk about this notion of adjacency. So we're going to talk about adjacency. So there's kind of two main terminologies we're going to have to touch upon. So adjacency of vertices. So this is adjacency is something we could talk about with among vertices. And incidence is where we talk about with edges. So if we want to talk about edges with respect to other edges or on vertices. So very often I would like to talk about the edges. The edges. So this is we're talking about the connectivity. So how can we talk about that? So these are going to be the two notions we're going to use here, is so-called adjacency versus incidence. So this is involving the vertices, this is involving the edges, or if, say, for example, I have an edge, like say I have U and V, and I would like to say this edge with that endpoint. I would like to have some way of talking about that, which incidence provides. So let's talk about adjacency first. Let's head over here. So I'm going to primarily focus on undirected graphs, but in the notes you'll find more terminology for directed graphs. But I will touch upon both of them. Okay. So what's adjacency mean? So if we're talking about adjacency. So what does that mean? It just simply means there is an edge connecting two vertices. So I'm just going to use broader terminology here at first, and I'll specialize. If edge UV is in a graph, then we'll say vertex, then vertex V is adjacent to vertex U. So in a directed graph, so in a digraph, V is adjacent to U if U is the edge U is directed from U to V. I must stress that in a digraph, adjacency is not symmetric, meaning that you can't just flip this around and say they're adjacent, because remember the arrow, the direction of the arrow on the directed edge. It gates me off from saying that. It prevents me from saying that. If U is adjacent to V, so I'll say adjacency is not symmetric in digraphs. What does that mean? That means that I would need an edge. Instead of it being from U to V, it has to be from V to U to say the other way around, right? In an undirected graph G, an edge UV in G implies U is adjacent to V and V is adjacent to U. So in the case of an undirected graph, the relationship of adjacency is symmetric. So it doesn't matter, I could flip them, it doesn't matter. So just as an example, I'm going to draw the graph I had earlier. I must stress there's no special meaning to the way I'm drawing this graph. I could have easily have placed the edges and vertices in different spots. The connectivity between them, the fact that two vertices are adjacent matters. That's what matters here. So for example, I could say that A is adjacent to B. I could say B is adjacent to A. I could say that F is adjacent to A. I could say A is adjacent to F. It's really not that bad at all. So that's adjacency. So we use this to talk about if there is a, very commonly in circles, we'll say if I have a vertex, I want to know very often about my neighbors. Those are the vertices that are connected by an edge to, and where I have the other endpoint. We'd say that all of these are adjacent. So for example, B is adjacent to A, C is adjacent to A, F is adjacent to A, and E is adjacent to A. These are all so-called neighbors of A. So the other relationship I want to talk about is incidence. So we say two edges, E and E prime, are incident if at least one endpoint of E and E prime is the same. So the way I would say this is one way I could say this, is I could say E is incident with E prime. So for example here, I would say that if I had this edge, the one that has two endpoints A and B, and I have this other edge AC, I would say that this edge, so if I called this one, I'll call it edge 1, and we'll call this edge 2, I would say edge 1 is incident with edge 2. Or if I want to give their proper names, I would say that this is edge AB, and this is edge AC. I can call this one E, I'll call this one E prime, and then E is incident with E prime. Or I can literally just give their names as edges. Another notion is the idea of talking about an edge in relation to a vertex. In an undirected graph, edge UV is said to be incident on. So notice the relationship I'm saying, incident on versus incident with. Incident on vertices U and V. So for example, if I have this edge with the endpoints A and F, I would say that this edge is incident on A and F. Just like this edge here, I would say that this edge E is incident on A and B. I can always talk about just a singular vertex as if I give you edge E, I could say that's this edge E is incident on A, for example. It's a way I could talk about one of the endpoints or both the endpoints in relation to the edge. So in contrast, if I want to talk about a directed edge in digraphs, an edge UV, remember the direction of the edge, it goes from U to V. So that means, so there's some special terminology for this, is incident from, sometimes we say that's leaves, it leaves, it's incident from U and is incident to or enters, so enters V. So there's a different set of terminology for if we want to talk about from and to, because it's a directed edge. But so that's the notion of adjacency and incidence. Now the next thing I need to talk about are a couple other concepts. So let's proceed. So there's a few other things. Now, most of the time when we consider things like graphs in this course, we will just be assuming quite a much simpler structure than what you could formulate all over the place with graphs. So most of the time we'll talk about undirected graphs, but like I said, there's other graph types. But I'll usually just assume we're going to talk about an undirected graph in most circumstances unless I say otherwise. But I want to bring up some other terms. So for example, you'll notice that in my example I gave over there before where I had two directed edges, notice that it allowed me to have more than one edge between two vertices. But notice that they were directed, which doesn't make much of a difference from our standpoint, but it might if we talk about an undirected edge, for example. So we have this notion of parallel or multiple edges. So these are often called multi-edges. So this is just simply when you have two or more edges with the same endpoints. It's a little squeaky marker. With the same endpoints. So always keep in mind how it's being phrased for you. So for example, if I have A and B, I would say that these two edges are parallel or these are multi-edges. Now, I can also introduce edges that only really have one endpoint, but we count it as two in some circumstances. It's the notion of a self-loop. So this is an edge whose endpoints are the same vertex. So for example, I could put an edge like this on vertex B there, and I would say that that's a self loop. That's a self loop. Now we got to talk about a multigraph. So seeing as I talk about multi-edges, it's very natural that I have to tell you what a multigraph is. So this is a graph that permits multi-edges. And usually when we talk about multigraphs, typically they also permit self-loops, but just be careful. And typically, self-loops. Finally, there's the notion of a simple graph. This is going to be something we're going to commonly consider. It's the idea of a simple graph. It's a little squeaky. I'm going to switch markers in a moment if it continues. So this is just simply a graph with no multi-edges or self-loops. So that means that so if I give you any vertices in this graph, if there's an edge, there's only one edge that shares those two common endpoints. Likewise, there are no edges that have two vertices as the exact same vertex in the graph as well. You'll find when we very often talk about algorithms, I'll usually talk about simple undirected graphs very often, unless I say otherwise. But many of the properties I'm going to talk about in a wee bit also apply quite generally. Sorry, I'm getting very excited here. So, let's talk about degrees next. Now, I'm not talking about academic degrees. I'm talking about the notion of a degree of a vertex, which is, it actually has a very lovely property for us that we can talk about. So it's a very cute property that we're going to talk about. So next we're going to talk about the idea of a degree. So again, I should have kept that graph there. I'm going to use it. So let me draw the graph again. Keep in mind, it doesn't have to be this graph. I'm just using it as an example. So I have A, B, C, F, D, and E. So I'm going to define the notion of a degree of a vertex. So in an undirected graph, let me put that G a little closer. In an undirected graph, the degree of a vertex V, which I'm going to denote, it's denoted as deg of V, is the number of edges my apologies, I inhaled a little dust there. It's not the number of edges, it's the number of incident edges. I knew I did something funny. Number of incident edges of V. So I must note, just as a note, that self-loops, because remember, a self-loop is just simply an edge that where both its endpoints are the same vertex. I must note that self-loops add 2 to the degree. So they don't add 1, they add 2, because the way you got to think about it is, imagine you have an edge. From the perspective of entering or leaving, you can also look at it like from one side, it's connected from one perspective to the vertex, and then it's connected to the other side. So it's like, it counts as 2 instead of just 1 if we talk about the degree typically. That's usually the convention that's being used when we talk about the degree. So let's do some examples where I play around with this a little bit. So let's do some examples. So if I give you the degree of, for example, A, what's the degree of A here? Well, let's look at how many incident edges are on A. So I got 1, 2, 3, 4. So I have 4 incident edges. How about the degree of B? Actually, let's do C. I feel like C. Let's do C. So if I do the degree of C, I have 1 and I have 2. I have 2 neighbors. Those are the number of incident edges I have here. Now I must stress that if I have multi-edges, you have to count those. So just keep that in mind. So in a simple graph, it's just the number of neighbors you have. So dag of C is just 2. Let's do another one. D. 1, 2, 3. 3. And the degree of E is just 1. Notice that I have only 1 edge that is incident on E. So I'm just counting the number of edges incident on the vertex. So, also there are notions of in degree and out degree you can define for a directed graph. So the so-called in degree so in a digraph, this is denoted as dag with a minus of V. So if I want to know the in degree of vertex V, I give it dag with a minus of V is the number of incoming edges. Edges to V. So remember, a directed graph, you have it where you have edges that they come from some vertex, they leave a vertex, then enter another one over a directed edge. So we would say that this edge right here is from this vertex to that vertex. I'm just counting up all, so if I'm counting up the in degree, I'm counting up all the arrows that are incoming toward my vertex. The out degree is very natural. If you think about it as the other thing it has to be. So the out degree in a digraph. And this is denoted with dag with a plus sign of V, like this. Is the number of outgoing edges from V. So for example, notice I have no outgoing edges from this vertex right here. So I would say that this has a 0 out degree. All of these other ones have 1 outgoing edge, so each one of these has out degree 1. So where am I going with this? Now, there's a very cute property that is quite versatile. It pops up sometimes when we talk about data structures and algorithms, quite often. It's just one of these cute properties that every once in a blue moon you use it, and it becomes very convenient. So I'm going to present a theorem to you. It's easily one of the simplest proofs in this course. It's called I'm going to refer to it as the handshaking lemma. Some people call this the degree sum formula. So it's called I'm going to refer to it as the handshaking lemma. So it's so simple, I'm just not going to even write out the proof. I'm just going to explain the argument. It's about, let's see, how many sentences is this? It's 2 sentences. It's a very basic counting argument that I can explain very simply for you. I recommend you check it out though. So what does it say? For any undirected graph. Now I must stress, this is true even when you have multi-edges and also self-loops in the graph. This is also true. So this is true for multigraphs too. Just as long as it's undirected. For any undirected graph, G is equal to VE. If I sum over all the vertices, so if I consider each vertex, and I consider its degree. So I sum over each one. So I go over each vertex, and I consider its degree. I add these all together in one bucket. This is exactly equal to 2 times the number of edges. Now, that's what the handshaking lemma is. It's a very cute but versatile property. So let me explain how this works. So think about it, instead of thinking of it like, oh, there's a sum with all the vertices. Think about it from a different angle. Look at it from the perspective of one vertex and then the other vertex. So remember, the degrees of the vertices. Remember, what's the degree? So remember, it's the number of incident edges on a given vertex, right? So imagine I'm at vertex D here. Each one of these, the incident edges are these, right? These 3 edges. So from the perspective of vertex D, you can imagine this like each one of these vertices is going to come out and shake the hands of each one of those vertices, like they're at a big party. So vertex D puts out his or her, whatever hand, well, it's a vertex, right? I don't know anything about the vertex's identity, okay? So I don't know. I'm going to put up my hand. I'm going to, well, I'm not going to put my on. Vertex D is. I don't know how D does it, but I'm going to put out the D's arm. It's going to shake each one of their hands. Well, from their perspective, if you asked each one of these people, they shook hands with D, right? But I want to know how many handshakes happened. So from the perspective of each one of them, they shook one person's hand. But if I ask each one of these people, if I imagine these as people now, well, this person's going to shake D's hand, shakes D's hand, and shakes D's hand, right? Well, what does that mean? Every single time I consider the degree of a vertex, when I look at the perspective of one of the vertices, I get the degree of the vertex, right? I ask, how many hands did you shake? They tell me that many, but for each one of the hands that they shook, they will report back that they shook D's hand too. That means I'm double counting. All my degrees are actually going to account for double counting of the edges. So it's every single time I do this. So if I consider vertex F, notice it shakes hands with D and also A. But from A's perspective, they also shook F's hand, right? So notice that the number of times I count this edge is twice. So the proof is a double counting argument. So the proof uses double counting. So it's a double counting argument. So I'll let you take a look at it. It's a very short proof. It's very cute. But it's a very cute property, but you'll find that it will creep up every once in a while and be like, dang, that's really cool. As I'm dying here. We're okay. We're okay. Sorry, I got very excited about the handshaking lemma. I'm just trembling here. So it uses double counting. But yeah, the big thing is that when I sum over all the degrees, I get a relationship with the number of edges in the graph. Now I must stress that the directed version of this also does have a similar relationship. Let me just write that over here. But yeah, the big idea here is that every time I count up the degrees of one vertex, there's going to be a corresponding vertex that's going to count that same edge again, but that'll be the incident edge from the opposing side. Is that kind of neat? So when I ask how many handshakes happen from the perspective of each one, it's going to be twice the number of total handshakes that actually happened. So I have also a similar property for directed graphs. For any digraph, G is equal to VE. So if I sum over all the vertices, and I do this over, I want to determine all the in degrees. Believe it or not, this is the sum of over all the in degrees is actually equal to the sum of all the out degrees. Which is equal to the number of edges. The argument's quite similar to the one I gave over there. Just the difference now is I have directed edges, which only contribute in one direction. But remember, from the perspective of each one of the vertices, remember I have two vertices. Remember, when I count the out degree of this vertex, it also, so if I count up the out degree, it goes 1 to the out degree. However, for this vertex, the in degree goes up by 1. Which essentially the same argument will work, just now I'm contributing each time I have an arrow going out. It adds to the in degree. Whenever an arrow is going out from my vertex, it adds 1 to the out degree. So they balance each other out always. So, I'm going to talk about just a couple other smaller details. I'm going to talk about, actually, let's talk about one last thing, and then we'll stop. So let's head over here. Let's talk about one last thing. I'm going to talk about complete graphs, and then we'll stop here. So, so let's talk about complete graphs. So let's talk about so-called complete graphs. So a complete graph on n vertices, which is denoted, so it's denoted as with a capital K with a subscript n, Kn, is an undirected graph, where every vertex is adjacent to every other vertex. So, just to give you some pictures, for example, K1 is a vertex with just one vertex. I just have one vertex. It's not very interesting. K2 is with two vertices. Notice that I have a single edge that connects both of them, meaning that every vertex is adjacent to every other vertex in here, which is quite simple. K3 looks like this. Some people like to refer to this as a triangle in some circles. So in graph theoretic terms, some people refer to this as a triangle because it looks like a triangle. It's K3. K4. So 4 vertices, every vertex is adjacent to every other vertex. This is K4. Remember, as I said, the way I draw these graphs doesn't matter too much, really, unless we need that specifically, like we're embedding a graph onto a flat surface or something like that, like for visualization. So for example, this same graph, I can also draw it like this. That's another way I can draw it. But notice that there's a way I could draw it without having any of the lines crossing that represent the edges. That's a nice property. Now, more generally, I can always build Kn by just simply doing this. So if I give you arbitrary n, I can have vertex 1, vertex 2, vertex 3, vertex 4, vertex 5, and all of these are going to be adjacent to each other. I'm trying to think if I missed any. Let's see, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Let's see. Sorry, 1, 2, 3, 4. We got 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, I got them all. Now, there's going to be eventually somewhere we're going to get Vn here, which is going to be adjacent to all of these. And all the way around. So I can show you how to build Kn. So this is what Kn will end up looking like for some arbitrary n. So a natural question is, how many edges does Kn have? Because keep in mind, if I give you a simple graph, the maximum number of edges possible has to match up with the complete graph, because notice that every vertex adjacent to every other vertex. So sometimes it's helpful to know an upper bound on the number of edges that are possible. So how many edges does Kn have? Well, we can pull out our double counting technique I mentioned the other day. Well, not the other day, the other moment ago with Handshaking Lemma. But it's not the exact same way I'm going to use it. Notice that if I pick any one vertex, it's adjacent to every other vertex. So if I look at each one of these, how many edges are incident on that vertex? Well, there has to be n minus 1 other ones, right? So there's n vertices. Sorry, there's n vertices, each with n minus 1 incident edges. Right? So this is me saying, okay, so these are all of the ones I consider, right? But there's a thing I talked about, double counting, right? Where notice that from this perspective, I counted this one, right? But notice that I also count it this way too, because I look at this vertex compared to this one. Notice that from this perspective, I'm also counting this edge. So I'm actually double counting the edges. So we have n vertices, each with n minus 1 incident edges. And so we are double counting edges. So if I wanted to know how many it must be, well, it's n times n minus 1. Keep in mind, I phrased this a little bit more carefully in the notes. I'm just trying to lay out the ideas here. You would actually phrase a proper sentence here. This is just me kind of giving you the ideas here. So I have n. I check each one of the vertices. I have n minus 1 neighbors, or incident edges, in this case. And I double counted them. So I divide by 2. So what does this say? It says, so here's the theorem. For any undirected, and keep in mind I'm saying simple, because I'm just assuming the graph is simple based on the definition we have here by how I define the complete graph. For any undirected simple graph, which I'll just assume it's a simple graph otherwise, m is less than or equal to n times n minus 1 all over 2, which is big O of n squared. And the final thing I want to say, final thing, is remember that construction I showed you, how I could take any one, I can take a directed graph. Say if I want to have a directed graph that represents undirected edges, you might ask the same question about if I gave you a directed graph. So if I gave you if I give you a directed simple graph, and I ask, I'm getting very excited here. If I give you any directed graph, I'm assuming it's not a multigraph. If I give you any such thing, what's the bound on how many directed edges are possible? Well, remember what I told you earlier. I could imagine each one of these undirected edges as 2 directed edges. So from our perspective, what we did before, where I counted up them and I double counted them, I get rid of the double counting because now it literally is that there's an edge from each perspective, like I was saying. So what does that mean? So it means simply in digraphs. So remember, I'm making some assumptions about what kind of graphs we're talking about. We're not talking about multigraphs. In digraphs, m is less than or equal to n times n minus 1, which is big O of n squared. So just keep that in mind. These are two helpful bounds to be aware of. We're going to stop right here. I'm going to give you the rest of the time here to make up for any time that has happened throughout things up to this point. I want to give that back to you. So when we come back, we'll start talking about paths and cycles, and then we'll talk about, I think I have a couple other smaller details I want to get into before I talk about representing of graphs. So when we come back, we'll talk about that, okay? So I'll say thank you very much, and have yourself a beautiful day. I'll see you later.